All right, last video for the series of method of joint problems. And the last problem that we did on the practicum session from last Wednesday. Now this one looks a little bit different than some of the others that we've done, but don't get concerned when things look a little bit different. We can apply the same techniques to analyze them. So here we've got a three-member truss. This time, though, this three-member truss is going to be supported on a wall instead of on the ground. So to indicate that I've got a wall here, I'm going to draw a vertical line with these little slashes next to it that represents the surface of a wall. And on that wall, I'm going to draw the supports for our truss. We'll put a pin support up here and a roller support down here. A line going between those two. So there we have a three-member truss. We'll have joints A, B, and C. And at joint C, I'm going to hang a 1,500-pound weight. So 1,500 pounds there. We'll put some geometry on this. The distance from A to C, make 10 feet. From A to B, we'll make that distance 20 feet. And to the peak, we'll make that distance 8 feet. So there's our truss. In the end, we want a table that shows us the load and the state of tension or compression for each of those three members. And again, just like all the other problems in this series, I'm going to keep 5 significant figures internally and then present my answers to 3 significant figures. Now, since our loads are in pounds here, I'll label my column pounds. And then we've got tension and compression. We only have 3 members here. We have AB, AC, and BC. Now, as always, we start these with the external problem. So let's draw our free body diagram of the truss from the outside. So from the outside, we have the truss isolated. All we've got is this truss floating here in the air. We've got our 1,500-pound force acting on it at joint C. It's a pin support up here at A. So we'll replace that with 2 reaction forces. We'll have RAX, and I'm going to assume RAY is up. And again, our traditional coordinate system, positive X to the right, positive Y up, and counterclockwise moments are positive. Now, B is a roller. And in most of the problems we've seen, the rollers supply an upward force, but a roller supplies a force perpendicular to whatever surface it sits on. Here, the roller is sitting on a vertical, so it's going to produce a horizontal reaction. So we have our BX there. We have a non-concurrent force system, so we have 3 equations. Our sum of forces in the x direction, our sum of forces in the y direction, and our sum of moments about some point. So let's take our x direction forces. We've got RAX positive. We've got RBX also positive, and nothing else. In the y direction, we have a positive RAY and a negative 1,500 pounds. And then for moments, picking a pivot point is usually the hardest part about the moment equation. And here joint A is not a bad choice. If we pick joint A as our pivot point, RAX and RAY will have no moment. Only the 1,500 pound force and RBX will have a moment. So let's deal with RBX first. Here for pivoting at A, the line of action of RBX is way down here, 20 feet away from A. So we'll have 20 for our arm times RBX. And acting alone, RBX would tend to cause everything to rotate counterclockwise, and counterclockwise moments are positive. So we have positive 20 RBX. Then we have the 1,500 pound force. We've got to look at the line of action of that 1,500 pound force and how far away that line is from A. That line is 10 feet from A. So our arm is 10 feet times the 1,500 pound force. Acting alone, that 1,500 pounds would cause everything to rotate clockwise, and clockwise moments are negative. To be in equilibrium, all three of these sums must equal 0. There we have our equations of equilibrium. The x direction equation, not much we can do with that right now, because we have too many unknowns, but the y direction equation we can solve pretty easily. RAY minus 1,500 equals 0. If you add 1,500 to both sides, RAY equals 1,500 pounds. So we assumed the correct direction. RAY is definitely up since we got a positive value. We'll fill that in over here. RAY is 1,500 pounds. We can use the moment equation to find RBX. The moment equation is 20 RBX minus 10 times 1,500, that's 15,000. Add 15,000 to both sides. And divide both sides by 20. And we get that RBX is 750 pounds. That answer came out positive as well. So that means our assumed direction was correct. So RBX is 750 pounds. And that's 750 pounds to the right. RAY was 1,500 pounds up. Now the last equation we have left is our x direction equation. So we used our y direction. We used our moment. Now we need our y direction equation. The y direction equation says RAX plus RBX equals 0. Well, RBX is 750. So RAX plus 750 equals 0. To solve this equation, we'd subtract 750 from both sides. So RAX is a negative 750 pounds. Now that came out negative. That means our assumed direction for RAX is wrong. RAX has to pull to the left. And if you think about it, it kind of makes sense. If you pull down on this structure with this 1,500 pounds of force, it's all going to want to pivot around B by pulling the structure away from A. So to react against that, A has to pull the structure to the left. The moment that we're creating here by pulling down at 1,500 pounds at C is trying to rotate everything clockwise. That force to the left is keeping everything in equilibrium. So RAX is 750 pounds to the left. So there we've got our external problem solved. Now, just like in the last problem, it's a good idea when you're making that jump into the truss and looking at the internal forces to redraw the free body diagram you used for your external forces, filling in the correct directions and values for the reaction forces. So we'll do that over here. That'll help us keep everything straight when we start to look at the individual joints. So RAX was 750 pounds to the left. We had 1,500 pounds up, and then we had 750 to the right at B. So now we can do our method of joints, and it's really up to you where to start. I would probably start at A or at B. A has a little more going on at it because it's got 4 forces acting at joint A. B is a little bit simpler because it's got 3 forces. C I'd avoid because 2 of your unknowns are at angles, which means you'd have sines and cosines of different angles involved there. It gets really ugly really quickly. I think I'm going to start at B this time. I'm starting at B because there are only 3 forces there. That means in my free body diagram, I'm only going to have 3 forces. And there's only one angle involved, the angle BC makes with either horizontal or vertical. We'll figure that out in a moment. So at joint B, I've got my 750-pound reaction force to the right. I'm going to assume that member AB pulls up. So I have a force due to member AB pulling up. Then I'm going to assume member BC pushes down and to the right. I'm going to need an angle. I'm going to pick this angle here. To figure out the angle, just kind of look at what you've got here off of the drawing. We can figure out that angle pretty quickly. This angle would be the same value. So let's figure out our angles here. We know this distance is 10 feet. This distance here must be 16 feet. Sorry, not 16 feet, 12 feet. You have 20 and 8, so that's 12 feet. So we can figure out the value of this angle by the inverse tangent of 10 over 12. It's always opposite over adjacent. So inverse tangent of 10 over 12, we get a value here of 39.806 degrees. Now that would be the angle to vertical. The angle I've decided I wanted to work with here in my free body diagram is the angle to horizontal. So that's got to be the complement to this angle. So I just subtract that off from 90 to get 50.194 degrees. Now, if you wanted to work with the angle to horizontal, you could certainly do so. Because I'm not on a whiteboard here, and I can't easily erase it and go to that. I've already made a commitment to use this angle, so I'm going to go ahead and do that. But I usually don't like flipping around with complements and such, and just like to use what comes right from the geometry. So 50.194 is what I've got there. Now this is a concurrent force problem. All the forces act at a single point. So we only have 2 equations. We have our sum of forces in the x direction and our sum of forces in the y direction. In the x direction, I've got a positive 750 pounds, and I've got a piece of FBC pulling to the left. So left is negative. I have FBC adjacent side to the angle I've got there, so that'll be cosine of 50.194 degrees. Vertically, I've got all of FAB, and I've got a piece of FBC pulling down. That'd be the opposite piece. Opposite goes with sine. To be in equilibrium, those two sums have to be equal to 0. The x direction is about the only one I can solve right away. So we'll write that down here. If I add this whole piece over here, FBC cosine 50.194 to both sides, my new x direction equation will be just 750 equals FBC cosine 50.194 degrees. Divide both sides by that cosine. And FBC comes out to be 750 divided by the cosine of 50.194, 1,171.5. And that's pounds. So again, rounding to 5 sig figs, so I get 3 good sig figs in my answer. So 1,171.5 pounds. That's member BC. Now, knowing that, I can go to my y direction equation and say that FAB minus 1,171.5 times the sine of 50.194 degrees equals 0. The number here comes out to be, if we go to the calculator, 1,171.5 times the sine of 50.194. I get FAB minus 899.97 pounds. So pretty easy to solve. Add 899.97 to both sides, and we get FAB is 899.97 pounds. So there we have values for the load carried by member BC and carried by member AB. What we have to determine is whether or not those are in tension or compression. Both of them came out positive, which means that our assumed directions for AB and AC are good. We just have to figure out what that means with respect to tension or compression. So this point represents joint B, and joint B is down here. Member BC is up and to the right. So if I sketch member BC in here, member BC looks like that. That's member BC. And member BC is pretty clearly pushing joint B away. Members in compression push the joints away. So member BC, we can go up to our table. Member BC is in compression and carries a load of 1,171.5 pounds. We can do the same thing for member AB. Member AB is above joint B. So member AB looks something like that. The force due to member AB points in toward the middle of the beam. Member AB is pulling joints A and B closer to the middle. That's our sign of tension. So member AB is in tension, and it carries 899.97 pounds of force. Now there's only one member left, and that's member AC. And I'm going to go to joint A for that one. So there's all the analysis for joint B to figure out what we needed there. Now we've learned everything we can at joint B. We've got to go to a different joint. I'm going to go to joint A again to avoid multiple members at different angles. It's hard enough to deal with one angle in the problem. Why want to deal with more of them? So one angle is enough. So let me go over to a different sheet here for joint A. So at joint A, we've got 4 forces. Fortunately, though, one of them we already know. We know member AB. We just have to make sure we account for that correctly. I'm going to try to keep the table on the screen here while we do this. So there's joint A. Joint A has 2 known forces on it. We had our reaction forces. We had 1,500 pounds up, and we had 750 pounds to the left. Then we have member AB. Now we calculated in the last part, that member AB carries a load of 899.97 pounds in tension. To fill that in correctly, we've got to get the right direction. Tension pulls the joints closer together. Tension pulls B up, but pulls A down. So while we found that we had 899.97 pounds of force pulling up at joint B, we have that same force pulling in the opposite direction at A. So we have 899, put that over here, 899.97 pounds pulling down. And then we've got member AC. So member AC goes off like that. Member AC we don't know the value of yet, but we do need an angle. This time I'm going to use the angle in here, since that's the same angle we'd get out of the geometry. The geometry is 10 feet across and 8 feet over there. The angle is going to be the inverse tangent of 10 over 8. So inverse tangent of 10 over 8, we get 51.340 degrees. So 51.340 degrees. We only have one unknown here, so we only need one equation. We could either do the sum of forces in the x direction or sum of forces in the y direction. And it's worth taking a couple seconds and just sort of thinking about which equation is going to be easier, or which one could be better in some sense. I'd like the x direction equation here because it's going to have fewer terms. In the y direction equation, I'd have 1,500 and I'd have this 899.97. And those are going to show up along with a piece of FAC. 3 terms. If I do my x direction, I've only got 750 and a piece of FAC. 2 terms. A little easier to deal with. So I'll do my sum of forces in the x direction. And the sum of forces in the x direction, I've got a negative 750, since that 750 pounds is to the left. And then I'm going to have the horizontal piece of FAC. Be careful here if you chose to use the vertical angle. Remember that we don't just get stuck on x is cosine and y is sine. Opposite and adjacent are what go with sine and cosine respectively. So here I've got to the right, so it's positive, some piece of FAC. It's the piece of FAC that is horizontal. It's essentially the opposite side of this triangle with FAC as the hypotenuse. Opposite goes with sine. So I have sine of 51.340. Of course, if you use the angle to vertical, then you'd be dealing with a cosine. Cosine of the complement ends up being the same as the sine. So either way works. Either way, you'll get to the right answer. Well, solving this one's not too bad. First, I'd add 750 to both sides. And that'll give me FAC times the sine of 51.340 equals 750. Divide both sides by the sine of 51.340. And we get that FAC first comes out positive. It's got to come out positive here. So we know we assumed it in the right direction. It wasn't too hard with everything we knew going on here. But FAC ends up coming out 750 divided by sine of 51.340. We get 960.47 pounds. And we have to interpret whether that's tension or compression. Came out positive, so we know our direction's good. This is joint A. Joint A is up here. So member AC is down and to the right. So member AC, if I sketch that in, looks something like that. And since we know the direction's right for AC, for FAC, member AC must be in tension, since the force that member AC exerts on the joint tends to pull the joint into the middle of the beam. So member AC is in tension. So member AC carries 960.47 pounds of force in tension. So that's the bulk of the problem. All that remains is for us to do our summary. So we'll keep the table here and work based on that. We have our truss, the external forces on it, 1,500 pounds. Our reaction forces, 750, 1,500. And 750. Now we'll just label each member. Member AB carries 899.97 pounds of force and tension. Rounding that off to 3 sig figs, we get 900. We can just label that with 900 point to make sure that it's clearly 3 sig figs. You could also write it in scientific notation, 9.00 times 10 to the second pounds. And that was in tension. We had for member AC 960 pounds, again having to use a dot at the end here to show 3 sig figs. 960 pounds, also in tension. And then we had 1,170, no dot there, 3 sig figs, trailing 0 doesn't count, pounds in compression. So there's our force summary diagram, rounded off to 3 sig figs. It's always a good idea to take a look at that and make sure the tension and compression makes sense, especially when there are only a few members. Kind of makes sense if you're pulling down hard on this end, it's going to put this one member that's down here at the bottom into compression while it tries to stretch out the member up at the top. So that explains the 960 pounds in tension. What's a little harder to see is why we have 900 pounds of tension in this vertical member. That's because as you're pulling down on the on joint C and putting member BC into compression, that compression is going to try to force this roller to roll. The roller is going to roll a little bit down the wall, causing member AB to stretch out. So the tension in member AB can be thought of as a way to keep that roller from rolling away. The compression in BC would tend to drive the roller down the wall. The tension in AB keeps it from going anywhere. So there we go. Last problem from the practicum. Next week, we're moving on to method of sections. And you'll be receiving email, if you haven't already, about how we're going to be doing that online.